Welcome back to Machine Translation. Today's lecture is about syntax and semantics. When we look at the history of machine translation, we observe that there is a pendulum that swings back and forth towards more linguistically motivated models or just purely data-driven models. For instance, when statistical machine translation emerged, they originally just were based on the notion of words. If you remember, we started with IBM Model 1. The only thing they really assumed about language, that there are words in sequence. And then over time, things like morphology were introduced with factored models, and then syntax-based models that used tree structures, and even then semantic representations were used in statistical machine translation. But then the pendulums make the hard swing back towards purely data-driven methods with the advent of neural machine translation. And that's still pretty much where we are. There have been some attempts to bring syntax and semantics back to neural machine translation, but none of this has really been much successful. So we'll go over a few of these efforts, but most of this class introduces just kind of background knowledge you should have about syntax and semantics, and to get some ideas how it might be applied to neural machine translation as well. So let's start with syntax. So the idea of building statistical models that operate on trees was a pretty successful reach-merge paradigm in the mid-2000s. So traditional statistical models operate on sequence of words. Both IBM Model 1 and phrase-based models fall into that category. However, many translation problems can be best explained by pointing to syntax. So for instance, if you look at translation from German to English, you find that there's a very systematic way how the verb moves during translation. Very often in German, the verb is at the end of a sentence and you have to place it after the subject. So knowing something about verbs and subjects is a useful thing to have. Also, there might be long distance agreement, for instance, between the subject and the verb, which may or may not be right next to each other, but they have to agree in count and maybe sometimes other properties like case. These are hard to explain in terms of word sequences, but they're pretty obvious and they have a direct connection in tree structures. So that's all led to translation models that are based on tree representations of language. As I said, this was pretty successful statistical machine translation. And here I'm writing open research challenge for neural models, and that is rather putting it gently. There were some efforts. It has been mostly abandoned at this point, but it's nevertheless worth knowing about. Okay, let's first give a little bit more background knowledge about what we talk about when we talk about syntax. So one way to look at syntax is the idea of dependency structure. So the idea of that is that at the center of a sentence is a verb. Here, the verb like. That is the center. And then it has arguments. There are words that depend on it. So you see here other words that point to like. So this is the subject pronoun here. And this is what we could call the head noun of the noun phrase of the object. So that leaves us with this structure here, which is a noun phrase. We now in dependency structure don't call things noun phrases, but it still kind of is visible because the other words here do point to the word lecture. So an interesting point to lecture. So another way to look at language is phrase structure grammar. So this introduces ideas like noun phrases, which I already just mentioned. Here's another one, the big man, a house. So in the previous sentence it was I and the interesting lecture. Prepositional phrases, which are essentially noun phrases with a preposition stuck in front of it. Then there are verb phrases. That's a rather maybe somewhat English-centric concept of a verb and its arguments, but not its subject. Then there are adjective phrases and other kinds of phrases. The way these phrases get formalized is with a context-free grammar. So this introduces a number of non-terminal symbols, which are labels for phrase structure and part of speech tags. So the terminal symbols are words. So we're building basically a derivation by applying a bunch of inference rules until we end up with just terminal symbols, which are the words of the sentence. So here's one example of a production rule. Noun phrase can be expressed as determiner and noun. That's one way to write a noun phrase. So that's the one that matches a house. So the production rules are non-terminal goes to a sequence of non-terminals and terminals. People who write grammars for just syntax structures typically only have rules that either are in the form of nt goes to nt plus or rules that are nt go to t. So they either produce a sequence of non-terminals, maybe a single non-terminal, or they produce a single terminal symbol. Okay, let's look at an example here. This is actually a sentence from the European Parliament, so you kind of get the flavor of the sentence. I shall be passing on to you some comments. So I run this through an existing parser tool, which is Collins parser, and this is the tree structure I'd revealed. So we have here a noun phrase, here we have a prepositional phrase, and then we have this verb phrase here, which is kind of built in stages. And then the sentence is the combination of this pronoun and a sentence, and a verb phrase forming the sentence node. Let's move on to semantics. So semantics is a very deep word. It deals with the meaning of sentences, and ultimately this is the grand goal of artificial intelligence. The machines do not just mindlessly process data, but they actually understand its meaning and can then, by their understanding, do higher level intelligence tasks. So that's kind of a rough vision. It's a bit of a fuzzy vision because what exactly is meaning? So this is maybe one caricature. So you want to have a computer that not only mindly processes data and follows instructions, but actually understands what you want. So a computer that understands you. There's also these concepts that get thrown around in discussions about artificial intelligence. So we have no doubt with saying machines are processing data. Are they processing knowledge? There are definitely a lot of aspects of artificial intelligence methods where the word knowledge is very easily used. You have knowledge bases and so on. And ultimately, though knowledge is not enough, you also need wisdom to kind of really understand what the knowledge tells you. Okay, I'll just throw out this example and I explain why I'm bringing this up. This is Eliza. This is a computer program that was written by Joseph Weizenbaum already in 1969. Just imagine what kind of computers were available in 1969. You can actually download the whole program or try it yourself. It's pretty short, obviously, since it was built for a computer in 1969. So this was a program that allowed people to talk to a machine, so chatbot. Nowadays, we would call these chatbots. So it's a chatbot from 1969. This particular chatbot tried to simulate a psychologist who kind of helps people with their problems, which is a pretty ambitious task for a computer to do. So here's a young woman comes in and says, men are all alike. And then Eliza asks, in what way? Young woman, they're always bugging us about something specific or other. Can you think about a specific example? Well, my boyfriend made me come here. Your boyfriend made you come here. He says I'm depressed much of the time. I'm sorry to hear that you're depressed. It's true, I'm unhappy. Do you think coming here will help you not to be unhappy? So that's a pretty impressive conversation. However, what Eliza actually did, it just followed fairly simple rules. Um, Here's a perfect example for that. So the woman says, my boyfriend made me come here, and what does the computer do? It just kind of repeats that statement back to the woman in terms of a question. There are also other responses like in what way, that can be pretty much said anywhere. Here is I'm depressed much of the time. And that gets rephrased in I'm sorry to hear that you are depressed, um, and so on. So what this method actually does, if you look at the code, it just kind of has some kind of rules to turn statements into questions and maybe some more fancier patterns, but it's really just a few patterns. And whenever it's lost, it says things like I see, or in what way, or tell me more about your mother. So people can very easily, the point here is that people can very readily attribute deep understanding to machines. So I don't know if you heard press reports about people, you know, getting so familiar with Amazon Echo and all these other tools that are around Alexa, um, and various other kind of online devices, Siri on the iPhone, that they treat them like a person, and they actually prefer them to a real person because they are much friendlier and don't really make much in terms of demands. So let's let's move on from this a little bit more philosophically excursion to actual really semantic translations problems we might have to deal with. So semantic translation problems have to deal with the fact that syntactic analysis may sometimes be ambiguous. So this is a German sentence, and if you do your syntactic analysis, you would say there's a noun phrase, the commission. This is another noun phrase, that's Vorhaben. Um, the plan, this means rejected. So the tree is pretty much, this is noun phrase, this is noun phrase, that's verb phrase, this is a sentence. So, but what does it actually mean? Well, there's an action here, and we need to find the person that's doing the action and then what the action is applied to. In German, the sentence is actually syntactically ambiguous. Both readings are possible. It could both mean that the commission rejects the plan or the plan rejects the commission. Just from what plans are doing and what commissions are doing, most readers of the sentence will assume that it means the commission rejected the plan because that just makes more sense. And that's where we are. What makes more sense? So what is semantic? Plausible. So the OSV reading, so that the sentence starts with the object, subject, verb, object, verb, subject, is semantically much more plausible. So how do we know that? How does we know this because we just know what about the world and have world knowledge, but how does the machine can possibly know this as well? So we need to have some kind of semantic model that produces semantically plausible annotation here. Let's start with lexical semantics. So we start with words and think about the meaning of words. And the most striking thing that immediately comes up is that some words have multiple meanings. There's a fancy word for that. It's called polysemy. And here is one of the classic examples there, bank, which is either a financial institution, I put my money in the bank, or the shore of a river, he rested on the bank of the river. So how could a computer possibly ever tell these apart? Because the computer sees these 4 characters in sequence either way. So how can it actually have different representations for these? Well, the answer is ultimately same way humans do it, by looking at context. Let me introduce one more concept here, which is homonym. So it's basically from a kind of processing perspective, rather indistinguishable from a synonym, but the distinction is made that if there are two completely different words that are spelled the same, these are called homonyms. So an example like can, which comes up in you can do it, and she bought a can of soda. These are actually really, they just happen to kind of sound the same, but they have absolutely no connection with each other at all. And it's not always clear now what the distinction between polysemy and homonymity is. And for a processing point of view, again, it doesn't really make much difference. In both cases, you have the problem that the word can has to be disambiguated. So how many senses are there? Can you actually then nail down maybe an inventory of senses and then process? Basically, look at each word occurrence, find the right sense label for it, and then process sense labeled words instead of raw words. That was definitely the vision of how to do things for a long, long time. But the first question, of course, is how many senses does a word like, let's say, interest have? So here's a bunch of sentences, and you tell me how many different senses the word interest is used here. She pays 3% interest on the loan. He showed a lot of interest in the painting. Microsoft purchased a controlling interest in Google. It is in the national interest to invade the Bahamas. I only have your best interest in mind. Playing chess is one of my interests. Business interests lobbied for the legislation. So how many different senses are there? 4 or 3 or what? So there's obviously this here. This is kind of this financial sense. This is here a very strange meaning of the word interest. It has something to do with a share in a company. Then the rest, all this is maybe also quite different because these are, it's kind of a motivated interest, kind of similar to here. That's not like curiosity or hobby. It's more like kind of how to say, kind of a established or maybe formalized opinion. And the others are somewhat in the curiosity meaning. Also, this is a hobby. Well, this is more, maybe more the other one. Okay, so it gets a bit confusing. So here's the answer from Wordnet. There was actually an effort, or is still extant, of basically formalizing all the different senses. And according to Wordnet, interest has 7 different senses. Senses are clustered into synsets, because a synset also then deals with synonyms. So a synset might have multiple words in it. So for instance, the sense 3 of interest also is synonymous with sake. So the synset contains sense 3 of interest and sake. So you can now read through all the definitions. So sense number 1, a sense of concern with and curiosity about something, the power of attracting or holding someone's interest, and so on and so on. Here's the right and legal share in something. So this is the buying a share in the company. Here is the interest rate kind of sense, and so on. So there's a difference made between a hobby, the reason for wanting to do something, versus here you have an interest group. So that was a distinction between I'm looking out for your interest, that was this, and then one business interest did something, that was this sense. Anyway, you can map these senses to the sentences in the previous slide, and actually for each of these senses there is one sentence. So for machine translation, the most relevant problem is that words often have different translations, and the reason they have different translations is because they have different senses. So in some contexts, one translation is the only appropriate translation. In another context, another word is the only appropriate translation. If 2 translations are equally appropriate, then that's because those translation words are synonyms of each other. So just to give you an example of what happens to the word interest when you translate it into German, You have a word like since, which has this financial charge meaning. You would use a word like Anteil if you talk about a stake of a company. But for all the other sentences, you actually can use the word Interesse. So arguably, according to this, if interest has 7 senses in English, the German word Interesse has at least 5 senses to cover all these. So for translation, we might have to make less distinctions. And it's also kind of a very, very elegant answer to the question, how many senses does a word have? Well, it has as many senses as it has translations. Just to give you some subtle sense about how languages differ in the senses they assign to things. For instance, if you would say, look at the word river in English, that's a pretty unambiguous word. Um, there are distinctions being made in French that are not being made in English. So there is here fleuve, is a river that flows into the sea, and rivière is a smaller river. Obviously, there are also a lot of words in English that describe smaller rivers, like a creek, or a bigger river, like a stream. But they're not connected with the meaning of where they flow into. They are connected really just with the size of them. So English might make, on the other hand, English might also make finer distinctions than a foreign language. So here's an example of a German word Sicherheit that I also used an example a few times earlier on previous slides, in previous lectures. So here are, according to the dictionary, the different translations for it: security, safety, and confidence. And especially the distinction between security and safety is rather subtle. Here's another great example for different senses, names of colors. So obviously the color spectrum is a continuum, and what range in the continuum gets which name is pretty arbitrary. There's no really hard rules why a language should have certain color distinctions. It's obviously deeply culturally embedded. So up here, you see an example how English looks. So there's a large range of the color spectrum is called green, another one blue, red apparently a smaller one, and there's brown and orange, which are kind of similar in a lot of ways, and so on. So these are color spectrums and names for them. Down here is a different language called Berino, and these are the distinctions that are made. So what you see here is, for instance, that most of the green and blue are merged together here into one entity, and there's no distinction here made between pink and red, and it also includes some of the orange. Here's another example from Japanese. There's a name Ao that actually changed its meaning in the 20th century, where it originally meant something between green and blue, and then there was a new word that came up with for green, which is called Midori, while Ao then really just meant blue. However, there's still traces of that. So if you have vegetables, you can call them in English also the greens. Did you eat your greens today? And in Japanese, you call them aomono, which are blue things, although they're actually green, but you see where that goes. Also, the traffic light go is viewed as blue. Okay. So one last word on senses. A lot of research in word sense disambiguation is focused on polysemous words that very clear, distinct meanings, like bank, plant, bet. It's a popular research topic. I have worked on that too as one of my first things in grad school. It's kind of, you do really deep stuff with the machine, word senses, meaning, and it's kind of a challenging problem. But however, maybe you shouldn't work on words like bank, plank, and bat, because most of the things that actually encounter in text are fairly close in meaning and hard to tell apart. So just give you here an example. area, field, domain, part, member. Um, they have a lot of similarities. Something a research area, a research field, a research domain, not a research part. Here's another example of using the word part and member. So she's a part of the team, that's a fine sentence. She's a member of the team, that's a fine sentence. The wheel is a part of the car, nobody's a problem with that. The wheel is a member of the car, you can't say that. So why can you use part and member here interchangeable, but here you can't use part and member interchangeable? Okay, another way to just purely just list the meaning of words is just to kind of group words together that have similar meanings into a structure. This is called ontology, or it's at least one of the key elements of an ontology. So you have things like dog, which then has subcategories like poodle and terrier, and then you can go up the hierarchy. And here, if you're talking about animals, you're using a lot of uh, uh, terminology from biology, canine. That might be still a word you might use here and there, which also includes wolves and foxes, and then carnivore, which then also includes completely different animals like feline and bear. Then you have mammal, although not all mammals are carnivores, and not all carnivores are mammals, so it doesn't quite work out as nicely. Actually, where there's a lot of biggest debate in these ontologies is always in the middle. It's like, how do you group these things in the middle? On the very top level, you just say there are entities, there are animate things and inanimate things and so on. There's a very broad categories, but then in the middle, things go a little bit haywire. So if people come up with different ontologies, they often differ a lot in this middle part. Okay, so we need to represent meaning somehow if you want to process it. And typically this is formalized where you say the word dog occurs in text, and now we want to get the meaning, and we're just going to write the meaning in all caps. So the meaning of word is writing the same word in all caps. Okay, we could also do something else by writing it as some kind of propositional logic statement, more on that later, where we say dog X. So X, there's now a dog X mentioned in the text. However, they are just kind of manipulating symbols here, so we're not really gaining much. What we would like to have is that words that have similar meaning should also have similar representations. And we also would like to do some kind of composition of meaning. So if you take the meaning of child and the meaning of female and put it together, we should get the meaning of daughter. So we would like to have that kind of operations on meaning representations. Here's another classic example, or at least by now it's classic. It's the meaning of king plus the meaning of woman minus the meaning of man should give you the meaning of queen. So how can we get that? So we already mentioned that we know the meaning of a word by its context. So why don't we actually put this to work and actually say, let's represent the meaning of a word by its context, by really just saying which context does it occur in. So here is the word bat. It actually occurs multiple times in the story. And let's look at the whole story, so the context of this word. And we get these kind of words. And certain words occur once, some occur multiple times. We're actually only listing here the nouns, verbs, and adjectives. And we're going to remove all these words like the and where and at, which are sometimes also called stop words, so we don't really need them. So obviously, if it's a longer story, then these counts are going to be higher, so we're going to normalize these counts so they all add up to 1. So this is then a distributional semantic representation of the word bat, at least how it occurs in this story, but you can then look at all the occurrences of the word and you basically get vectors like this. So when you look at, so this looked at all the words in the sentence, we might also just look at directly neighboring words. So by now we have moved on to word embeddings, where we're basically doing the same thing. We also look at the context of words and derive representations. And here are some word embeddings that have been produced. which puts words that are close to each other in meaning right next to each other. So playing, scoring, winning, losing, they're all similar in meaning and they're put next to each other. Okay, so word-sensitive disambiguation is the task of basically figuring out what the correct sense of a word is in a particular context. So we basically can frame this as a supervised learning problem where we say we basically annotate some data, and sometimes we annotate the word plant with like plant factory for chemical plant versus a flower. So what are the features to do this? Well, you look at directly neighboring words, so plant life, manufacturing plant, assembly plant, plant closure, plant species. Already as a human, we can say, this is the bio meaning, and this is the whatever the production factory meaning. It's called factory meaning. This is the factory meaning. This is the factory meaning. This is the bio meaning. So we can often figure this out pretty straightforwardly. So here are some features that people used. Any content word in a 50-word window, syntactically related word, syntactic role and sense, topic. So this means is it the subject of a sentence or the object of a sentence, topic of the text. Maybe you have a topic classifier that first groups text into topics. So this is a sports article and so on. We can also look at more granular features like the part of speech tag that's assigned to it or surrounding part of speech tags. Okay, let's move on a little bit with semantics beyond words and look at subcategorization frames. So these come up when we look at the meaning of verbs. So we have here reject as a verb in here, and there is an effort to basically figure out what the meaning of verbs is. Verbs are kind of nice because they're relatively finite. New verbs do not necessarily come up all the time. Yeah, okay, people are suddenly tweeting, which they didn't used to do, but it's much less productive than nouns. Okay, so there's a prop bank that just says that here is one possible subcategorization frame for verb. So it has one argument, which is the rejector, which can also be framed as a generic form of agent. Yeah, one word to this here. So these things got names. So you can call some of these roles agents and themes. However, in prop bank, they're kind of, once you do this, you run into problems. What do you call when agent and what do you call when theme? So they did actually a much simpler thing. We're just saying each verb has a list of arguments and they have numbers, and that's it. So arg0 of reject, that's something that means something to reject, and it might mean something completely different for view or investigate or whatever. So it has a subject, a rejector, agent, I would say, a theme, that's a thing that's being rejected, and then it might also have an attribute. So then that allows us to ask the question, if you have the word reject, is plan a typical arg0? So how often does plan occur as the arg0 of reject? And that's probably not as happening as often as commission being the arg0 of reject. So how do we get there? So we need to do first dependency parsing, and then if you look at the dependencies of a verb, we can basically label them with these names, arg0, arg1. So we first do a dependency parser, and then we also have labels for them. And then we can basically figure out reject subject plan. That should say that's a kind of a bad assignment, and reject subject commission is a good assignment. So maybe this is a bad assignment. This should be arg1 and this should be arg0. Okay, let's delve even deeper in the representation of semantics, which is logical form. So this is the idea of representing the meaning of language in logic. The simplest logic is first order logic. Here's a classic example. Every farmer has a donkey. It actually is ambiguous. It has two readings. The first reading is for all farmers, X, there exists a donkey Y, and X owns the donkey Y. So that basically means that each farmer in the world has a donkey. That is their donkey. Here's another meaning. There's only one donkey. So there is a donkey, and for all farmers, they own that one donkey. So this a donkey is actually only a single donkey in the sentence. So every farmer has that donkey. You know, that's maybe a bit hard to even grasp, but if you think about every farmer has a god, maybe that makes more sense. It's more intuitive reading. So does this actually matter for translation? And one answer is typically actually it doesn't, because if it is ambiguous, then the translation can be also be equally ambiguous. So you just have to basically, if you just make a surface level translation, the ambiguity is even preserved. You never actually have to resolve it. So here's an example I had in a very, very early introduction slides. Whenever I visit my uncle and his daughter, I can't decide who's my favorite cousin. So how do you do this with logical form and inference? So now we actually moved on to a slightly more sophisticated form of logic. So we have a female D, so we kind of introduce now names for things. This is D, this is U, this is C, and then this is I. So this is kind of introducing just nice proper formal labels for the nouns in the sentence. And here is kind of basically just stating the same thing. So there is a D, which is female. D is female, that's what we know about D. Then U is the father of the daughter, so the uncle is the father of the daughter. So you have an uncle-daughter relationship here. And then he is also my uncle, so there's an uncle and I relationship. And then there's a cousin relationship between I and C. So this is now where world knowledge comes in. So if you have an I, a U, and a C, and you have and U is the uncle of I, and U is the father of C, then we can figure out, so U is both is the uncle of I and the father of C, and therefore I and C are cousins. Probably should fix this here. This should be U, D. So here's a hypothesis we have in the sentence that C and D is the same, and it's consistent with the given facts. And therefore, we can also infer that we know that D is female, therefore C is female. So we kind of know that C and D are the same thing, so they're both female. So if you put this into our machine translation system, probably at some kind of pre-processing process that adds additional information to the sentence, we can then translate this properly into languages like German and French. Another ambiguity is scope. So this is a structural ambiguity. It's not a word meaning ambiguity. Here's an example: green eggs and ham, which some people like or some people don't like. And what's actually unclear is the ham green? Definitely the eggs are green, but the ham, there are two different readings. Either you say it's green eggs and ham, or you say what's green is eggs and ham. So first you should group these two together and the other one. So Words like and are really, really notorious. They kind of blow up the interpretability of sentences. So, and what they kind of cover, the scope of what they cover. So, do they cover just the neighboring two words, or do they cover this whole sequence and this sequence? That is the question. And that is often incredibly ambiguous. And not necessarily for a human reader, but for a machine. So how do you translate that into Spanish? So if you just translate this straightforwardly, huevos verdes, jamón, that would mean, this is just really the only thing that interesting thing that happens here is that the green and the eggs switch the meaning because adjective nouns are flipped on a different order in Spanish. But that meaning then really means that only the eggs are green. So maybe what we should do instead is produce a translation where we put the verdes here at the end, and now you have the same ambiguity where verdes definitely talks about the huevos, and then it's unclear if it also covers the jamón. So is this Y again? Is it connecting just these two words, or is it connecting here this phrase? So machine translation should preserve this kind of ambiguity. Okay, let's move on even higher in the linguistic analysis all the way to discourse. So one way this shows up in translation is that there are ambiguous discourse markers. So the word since has both a conditional and a temporal meaning. So in the first sentence, since you brought it up, I do not agree with it, that's definitely more a conditional meaning. So here we could really replace it with because. Because you brought it up, I do not agree with you. While the second one is more a temporal meaning. Since you brought it up, we have been working at it. So there you can't just, because you brought it up, we have been working on it. Well, maybe that's a different reading. So it's basically, since the time you brought it up, have we working on it? Or is there a reason that you brought it up that we have been working on it? So how do you translate? In a temporal sense or the conditional sense? Discourse relationships might actually be also impressed much more implicitly than just with a particular verb. Here is one example: wanting to go to the other side. The chicken crossed the road. There's a very clear implied um, discourse relationship here where the chicken crossed the road and this is the reason for it. So, and you could also put the word because here, except then you have to change a little bit the sentence structure, because it wanted to go to the other side. The chicken crossed the road. That basically is the same meaning. So in English, you can do with this particular odd construction, but maybe in other languages you can't. You actually have to choose the word because. So where do you get that? So you have to actually kind of now make up a word like because in the other language. A bit word on what people have done in discourse relationships. So first of all, you come up with a list of discourse relationships. Here's a whole list: circumstance, antithesis, concession, solutionhood, elaboration, background, enablement, and so on and so on. And then you have a hierarchical structure. So the nice thing is we had tree structures before, and now we can also have tree structures over not sentences, but clauses or elementary discourse units. So if you have a sentence, it might have multiple clauses in it, or elementary discourse units, and they have relations to it with each other. So here it starts with the projections are in the neighborhood of 50 cents a share to 75 cents. And then there's a comparison, compared, it actually says compared with a restated $1.65 a share a year earlier. And then here, this is a circumstance relationship when profit was 107.8 million on a sale of 435 and so on. So there have been efforts to build these kind of trees for documents. So then you have discourse tree bonk. But actually people have a hard time with these kind of definitions. And there's actually pretty low inter-annotator agreement. So it's not quite clear where that is heading. Let me now mention the last thing that has been attempted in statistical MT to move beyond syntax into semantics, and that is called abstract meaning representation. It looks like this. So it's basically a formalization of the semantic of sentences. It brings a lot of the things together that we already mentioned. So you have actually directly borrowed from prop bank the the subcategorization of verbs. So you have the verb look here, and it takes an arg0 and an arg1 and also has a manner. So then you look at the sentence here. He looked, so we know he is the subject. So this is arg0 at me. So this is then what is being looked at, and that's arg1. So how is it formulated? Well, it uses actually the words here and then introduce variables for it, which may be reused. And you actually see it here, the word H and I is being reused here. How does that happen? He looked at me very gravely because he put his arms around my neck. Okay, so that's the second sentence. So there's a put action, and here it just says and. So these are just combined with the and. So the discourse relationship is not labeled. It's really just heavily puts in the subcategorization relationships, and also most critically this co-reference here. So the point of that is that it abstracts some syntax, and when you have a sentence like this here, where you say there's a look action, and he is a looker, and I am the one that's being looked at, and then there's a manner, which is grave, and the degree of the graveness is vary. You can have possible English sentences. He looked at me gravely. I am looked by him. I looked at by him very gravely. He gave me a very grave look. They all should render into this meaning representation. So all these should have similar translations. And to enable that, we might first process it into this meaning representation. Okay, so how do we actually now use all that information in building better machine translation systems? So one idea is when we build machine translation systems, maybe we should add linguistic annotation to the input sentence and the output sentence, and then therefore that gives us better translation disambiguation abilities. So we could want to improve neural models with linguistic information. So we could have add linguistic annotation to the input sentence, and we can add linguistic annotation to the output sentence. Or we can even go further and build linguistically structured models. There's been work on all these three things. So linguistic annotation of the input. So one nice thing about neural models is they're very good with rich context. We can just throw more inputs at it, and they don't really have any problem with it. They've pretty gracefully consider that in predictions or ignore it. So the prediction currently in neural machine translation is conditioned on the entire input sentence and all previous output words. And that's obviously a lot to condition on because this entire input sentence and all these previous output words have never actually been seen in this combination ever before when it translates a sentence. So it's very good at generalizing about what of these various inputs is actually important. So adding more information as a conditional context is therefore very straightforward. So what kind of information would you want to add? You could add part of speech, lemmas, morphological properties, syntactic phrase structure, syntactic dependency, semantics. So here's an example how this might look like. So the girl watched attentively the beautiful fireflies. That's the sentence as it is presented to us as humans and to the machine translation system as we had it before. But we could do the following analysis. We could say that's the part of speech of these words, like the determiner. What is the lemma, which most time is the same, but here watch for watched. There might be morphological features, for instance, this past tense. There are things like noun phrase, where you have here a beginning of a noun phrase that continues for 2 more words. Here you have a beginning of a noun phrase that continues. Then here you have a verb phrase that begins and continues for a few words. Then you have the syntactic dependency, so you can just basically say for each word what its dependent are. So this is the subject. The subject here has the word watch as dependent, what it depends on, and also attentively and fireflies all modify the verb. So, and so on. So here deeply the semantic roles, actor, manner is a modification, patient, but maybe also have semantic types, like this is a human, it's a viewing action, this is an animate object. So you can actually add all these. So each property can be encoded as a one-hot vector. So the input then is not just a one-hot vector, but a concatenation of one-hot vectors, where each of these individual one-hot vectors stands for one of these categories. So we can add all this, and the question is, do we need to add all this, or can this be discovered by the machine learning itself? Okay, let me rant about this at the end a bit more. Okay, we can do the same thing at the output, so that such annotation might also be useful for output words. So this may then support more syntactically and semantically coherent output. And actually in statistical machine translation, where adding syntax was most successfully was in the output, because it enabled to produce not just well-formed sequences, but also well-formed tree structures, and therefore often had more grammatically correct translations. So this is the output as a syntactic structure. A tree is a bit hard to always put in a computer, but one simple way to put it into a computer is in this kind of linearized structure. So this is now just basically drawing this as a tree in terms of brackets. So, so the noun phrase here, just to give you the example, it has these subnodes, so they get put into brackets, and then you have the noun phrase around it, and that gets put into this bracket here. And therefore, this tree structure is fully identically represented in this linearized way. And you can actually prepare all your training data this way, put this in as your training data for the input, as training data for the output. You're making the argument that if this is the output, then a machine translation system has to produce. It's more likely produce syntactically correct output. There has been some evidence that that is actually the case. And these ideas were kind of explored a few years ago, and then nobody really has followed up on it, and things got forgotten. So we can also then go one step further and have linguistically structured models that do basically during translation the same thing as what a parser would do. So syntactic parsing is also now handled by deep learning. So to build parsers, you might need a bit more complicated models that actually build an output structure that is a well-formed tree, that is guaranteed to be a well-formed tree. So there's something called left to right push down automata that is being used for that. So it has to maintain a stack of open phrases. So if you look at the previous sentence, so whenever you open something early, a work, so you also you have to start a sentence node and so on. You kind of need to keep track of what you opened here, noun phrase, noun, what you opened here, and then here you started prepositional phrase. So all these things you might have to keep track of. So that's the stack you use, and then each step starts, extends, and closes a phrase. So you can basically think about this in terms of sequence of actions that are being done. Let's look at another area where some understanding of a translation process could be integrated into improved models for neural machine translation. we start with guided alignment training. So we already have this attention mechanism, which is pretty well motivated by the linguistic fact that each individual output word is often fully explained by a single input word. So we could support training by having externally generated word alignments that enforce this kind of principle. So we first generate word alignments with the IBM models and then bias attention to these alignments. So the way we can do this by introducing an additional cost function. So let's say we have given to us an alignment matrix A from these IBM models. So just to get the formalism right, that gives us a bunch of alignment points between word J and word I. And while we are training, our model comes up with an attention weight, also between I and J, and we basically make sure that these match up, so that either both of them are 0 or both of them are 1 or close to 1. So that's our cost function. So one useful byproduct of this, and maybe the actual ultimate purpose of that, is that we will get in the output also a word alignment where the attention mechanism mimics this alignment functionality. So here's actually what we get out of attention models. So this is a recurrent neural network where you see attention that is being paid by here now producing the German words. Should I just start with that? So the German sentence starts with a determiner, which actually doesn't have any equivalent in the English. It's somewhat connected to relations. At least that's the same noun phrase. Then you have Beziehungen, which means relations, and the attention mechanism reveals that pretty clearly. Then you have Zwischen, that's for between, Obama, and so on and so on. Some of these words, the attention mechanism is a bit fuzzy. So you have here seit, means 4 years, and so on. What is written in these blue boxes is the human annotation for attention. Actually, this is not the human annotation. This is annotation that was computed with symmetrized IBM models. So it actually is a bit faulty here. Otherwise, it often matches up pretty well. And the areas where it doesn't match up very well, it's also a bit ambiguous what the alignment should be. So have been strained. It doesn't have a clear equivalent in the translation. One odd thing actually worth pointing out is with the attention mechanism at the end of a sentence, it just kind of goes haywire and assigns attention weight all over the place. Okay, so we basically during training want to enforce that the attention mechanism follows the word alignment with this cost function. Okay, one more thing we can do then on top of that is properly modeling coverage. So what can happen in translation is that it overgenerates or undergenerates. There's also a real example of recurrent neural network model where the translation didn't skip part of the input here. So in order to solve the problem, the social housing alliance suggests a fresh start. A fresh start actually doesn't get translated. What happens instead is that it kind of goes a bit confused here, where it really should just translate social housing, which it didn't even translate in any accurate way. At least the word social is here, but building is education, not housing. And then it kind of produces all these, the enterprise of the society for social education. None of this has actually anything to do with the input. So this is what happens in translation. So what we can keep track of is how much attention is paid to the input words. And what we notice is, yeah, often that seems to be kind of in the right range, but here obviously you have this opening parenthesis that was way too much paid attention to when generating a slew of words here. And on the other hand, down here, the words here at the end, no attention was paid to at all, or very, very little. A bulk of it really just coming when it produced the period at the end. So that's something we can observe during decoding, and then maybe also say, hey, that's something that went wrong here, and that shouldn't have happened. And how can we fix this? So I have to say that neural models are generally very good at translating all the input words, but since it doesn't actually have an explicit coverage model, nothing really forces it to do that as we have done in statistical machine translation. It does sometimes fail. So the idea is either to enforce coverage during decoding or integrate a coverage model into the neural model. So this is what we could do during decoding, during inference. So during decoding, we can basically keep track of the coverage as we've done on the previous slide illustration. And then we can basically see how much overgeneration and how much undergeneration happens. And add a penalty function to score hypothesis. So you discount hypotheses that either overgenerate or undergenerate. So another idea is to extend the translation model. So we could, during training, also have a vector that accumulates coverage for input words to inform attention. So we have the raw attention score, which is informed by the decoder state and the input word. And now we add additional conditioning on coverage that has happened so far. So that would then hopefully move away attention from words that already received a lot of attention before, which is accumulated in coverage. So here's the cost function of that. So we can then also integrate kind of this coverage tracking in the training objective. Okay, let me finish up with a bit thinking about is this actually heading in the right direction? So this lecture reviewed a lot of concepts in syntax and semantics, and then it was hinting at methods that integrate these kind of ideas, coming from linguistic intuition into neural machine translation models, either at training time or inference time. So what we basically had here is a bit more of an engineering approach, where we identified weak points in the current systems, for instance, that it fails to translate part of the input sentence, and then develop changes to address them. And opposed to that is to just really put all your faith in machine learning. So if your model doesn't work well, maybe just get a deeper model, maybe play around with hyperparameters. Just generally have more robust estimation techniques. Figure out is a problem due to overfitting or underfitting or any other adjustments you can make. We are definitely in a situation where with neural models, this engineering approach is much harder to do because it's much harder to figure out what is actually happening inside neural models. So there's not a tweak that can easily apply. There's not a way we can look at the model and say, yeah, that number there shouldn't be 0.1, it should be 0.3. That'll fix it. So we can't really do that. So because of that, we are currently, most of the research really takes place in this space here. So everything I talked about today, yeah, that should be on the back of our mind. And we should remember that whenever we do error analysis and think about how to build better models. But to be quite honest about it, none of this currently has much currency and influence on how things are being done. And that's what I leave with today, and tomorrow in the next lecture we will look at current challenges to neural machine translation, so problems that haven't been solved yet. So that's it for today.